Good afternoon, ladies and gentlemen. Welcome to today's lunch hour lecture. My name is Jack Ashby from the Grant Museum of Zoology. I'm very pleased to host today's talk and to welcome Professor Lars Stixrude, who is Head of Department for the Department of Earth Sciences here at UCL. His research is based on understanding large-scale planetary processes by studying atomic-scale physics of planet-forming materials. And a current research project, Molten Earth, is looking at doing just that with the materials of the young Earth, which perfectly places him to give today's talk. How did Earth begin? If you could join me in welcoming Professor Lars Stixrude.
Okay, thank you very much. Well, this is a question that I think has fascinated humanity down through the ages. Origin myths of order, of evolving out of chaos by one form or another. To me, personally, it's also an interesting question because it came to science rather late. For most of the history of geology, for a large part of that time, it wasn't considered to be a valid scientific question. And it was only in the 20th century, with the discovery of radioactivity, that it became a truly firm scientific question to be answered by science. So I want to share with you some of that history before getting on to the sort of more recent developments in radiochronology, in planetary accretion, and in the physics of molten rock, silicate liquids, that have changed our view about the beginning of the Earth and the implications for the Earth as it is today. So this is just one example of a creation myth. This is from ancient Egypt. This is from the Book of the Dead that was on exhibit at the British Museum recently. And we have the sky god, Nut, and the earth god lying at the bottom here, Geb, and the god of the air, Shu, supporting the sky. One of the things that's striking about many origin myths, apart from our own, is that time is sort of indefinite. These myths are timeless. I mean, these gods could have been frolicking around for billions of years before the first human appears in the creation myth. They tend to show up much later, and there's a lot of activity going on before the humans show up. And even once they do, the timeline is not very definite, it's not very precise in terms of durations of time or even sequence of events somehow. And in our tradition, of course, in our religious tradition, Judeo-Christian tradition, it's very different. The story of the origin of the Earth that appears in the Old Testament is very definite in terms of its timeline, and I think this is something that distinguishes it in a way that's very interesting for geology, I think, and for the history of development of geological ideas from many other creation myths. There was a guy by the name of Archbishop Ussher, the primate of all Ireland, who collated a large amount of information and developed a very exact chronology of the creation of the Earth, setting the date for the creation of the Earth as October 23rd, 4004 BC. So he really nailed it down. This was based on scholarship of ancient languages, of the Bible itself, also of extra-biblical sources, and then taking all the very detailed information that's in the Old Testament about lifespans and births and succession of kings and so on, and working out this date of 4004 BC. Nowadays, of course, it's common for scientists to scoff at this effort entirely. If anything, maybe give him a pat on the head for knowing his Greek and Hebrew and so on. But I think, actually, that his influence was quite beneficial at the beginning of geology, and this is very counter to most accounts of the birth of geology, who usually go about saying that if only those geologists could have gotten their nose out of the Bible, then they would have been able to see what was in front of them out in nature. But sometimes you can only see what you're prepared to see. And the thing about Ussher's chronology, which was very influential and appeared in the standard version of the Bible into the 1970s, actually, it also influenced geologists a lot. And it gave them something to shoot at. As they were going out looking at rocks, they started to ask their questions. So to accumulate 100 meters of sediment, which is now sedimentary rock, is 6,000 years really enough? Or do I really need more than that? And how can I prove that I need more than that? It did take a while to get over this idea that the Earth was 6,000 years old. And speaking here in the Darwin Lecture Theatre, Charles Darwin's professor of geology at Cambridge in 1825 said in a textbook that, well, of course, we don't need to take the Bible as what's written in the Bible as literal truth, but when we go out in the field and look at the rocks, it just so happens that what we see in the field is completely consistent with the biblical account and with Archbishop Ussher's chronology. So I think the question of how did Earth begin got tied up with the Bible and the literal interpretation of the Bible in a way that for a long time discredited the question entirely. And I'll come back to the guy who most profoundly did that. But let me first turn to Mark Twain, who was alive at the time that this debate was really heating up about how did Earth begin and is that even a valid question to ask. He was very interested in these debates and wrote about them. And there's a little bit of it, there's a little snippet of it in Huckleberry Finn, which I find just really charming. And so let's join Huckleberry Finn and Jim for a moment in what must have seemed to them like the Garden of Eden, and being very positive about life on a raft. And Huckleberry says, we had the sky up there all speckled with stars, and we used to lay on our backs and look up at them and discuss about whether they was made or only just happened. Jim, he allowed they was made, but I allowed they happened. I judged it would have taken too long to make so many. So I think this idea between an actual process, making objects like the Earth and the stars, or whether they just happened by something magical and timeless, was still very much an alive debate in the 1800s when Mark Twain was writing. Well, I mentioned that this whole idea that the Earth had a beginning at all was discredited by geologists initially, in fact, by the founder of geology. His name is James Hutton. And one of the remarkable things about many English scientists of the time is that he had a wealth of practical knowledge. He had his own farm, and one of the things he noticed is something called, what we call today, the paradox of the soil. So he noticed that soil from his farm would erode away and go into rivers and eventually out to the sea, and he wondered, so if soil is being removed from my farm, and yet my farm is still viable year after year, soil must be being added to the farm as well. And that soil must come from the erosion of mountains. And this process must go on for a very long time. And if it goes on for a long time, then eventually the mountains will be eroded, and all of England will be eroded. And yet there's still land today. So as land is being destroyed in one place, it must be being born in another by volcanic activity or whatever. He was very influenced by reports of Etna and Vesuvius and so on. And so what he saw is, in his words, in the geologic record, no vestige of a beginning, no prospect of an end. He saw geologic time as an endless cycle, an endless repetition of the same processes of erosion of rock and rebuilding of rock through volcanic processes over and over again through ages uncountable. So to him, how did the Earth begin was not a scientific question at all. This is the most famous outcrop in geology. This is Sicker Point in Scotland. And you can interpret this with one very simple principle, and this was articulated by Steno, a Danish scientist in the 1500s actually, and that is that most rocks that we see at the Earth's surface are sedimentary, and that means they start their life as horizontal layers of sediment deposited underwater and eventually lithified by great pressure. And so what you see here is a sequence of sedimentary rocks, and you see two different sequences. One in which the layers of sedimentary, the layers are now vertical, and the other, on top of that, the layers are nearly horizontal. So this one outcrop represents at least two of Hutton's cycles. First, that lower series of layers were deposited underwater, then uplifted, turned on their side, then eroded away, then submerged underwater again, and then more sediment deposited on top of them, and then the whole thing lifted up into the sky again for us to see. So this was the sort of paradigm of his view of these endless cycles of Earth's time. Along came a guy named Lord Kelvin, who the temperature scale is named after. He made many contributions in physics. One of them was he also made a very important contribution to the age of the Earth. He said, wait a minute, Mr. Hutton and all of his followers, you can't have that. What you're talking about is a perpetual motion machine, which is physically impossible. It violates the laws of thermodynamics. You would need an infinite source of energy to keep these cycles going for an infinite amount of time. And that source of energy just doesn't exist. The other thing he did was he calculated an age of the Earth. And so the age of the Earth came back into scientific discussion with this calculation. He did a very simple thing. He said, let's assume the Earth starts out very hot, and let's imagine that it loses heat by conduction. And as it cools, it loses heat more and more slowly. And eventually, it'll get to the point where it's losing heat just at the rate that we observe the Earth is losing heat today. And you can calculate how much time that takes, given his assumptions. It's a problem that any freshman first-year physics student can do. It's very straightforward. And he got an age of something like 50 million years, okay? A lot older than Ussher's estimate, obviously, but certainly not infinite amounts of time either, as Hutton had wanted. And even 50 million years at the time he made this calculation, this is now the late 1800s, made geologists quite nervous, and biologists also. Charles Darwin, for example, recognized very quickly that in order to have evolution by natural selection and to see all the fossil species that he knew about in the geologic record would probably take longer than 50 million years. Well, Kelvin's calculation was absolutely correct as far as it went. In the larger scheme of things, of course, it turned out to be wrong because there was something he didn't know that nobody knew, and this is radioactive decay. This was only discovered at the very end of the 1800s and really only applied to the Earth a few decades after that. Okay, so take a deep breath. Most people know what you're breathing is mostly nitrogen, a bit of oxygen, and what's next? Now, most people think the next most abundant thing in the air is CO2. I think partly because of the concern that we have about CO2 and global warming today, and rightfully so. It turns out the next most abundant thing in the atmosphere is not CO2 at all. 20 times more abundant is argon. Now, the argon that you just breathed in, almost all of it is from radioactive decay, actually. It's from radioactive decay of potassium, which is a pretty common element in the Earth, and decay of potassium is a major heat source, driving all the processes that we see on the Earth today. Well, radioactive decay is a heat source, which Kelvin didn't take into account, and which completely falsifies his calculation and allows for a much, much older Earth. One is very comfortable then with the modern estimate of 4.5 billion years because of this extra energy source. The other thing, of course, that radioactive decay did for geology is it allowed us to quantify, really, for the first time, questions like, how did Earth begin? We can actually begin to put numbers on how old the Earth is. And potassium argon has a very long half-life, and that's one way to do it. Turns out the age of the Earth is best measured by uranium decaying to lead. And we do get this value of about 4.5 billion years. Okay, so radioactive decay gives us more than that. It allows us to do a lot more than just measure the age of the Earth. It can do that, but it can do a lot more. And one of the things it can do is it can tell us about some of the very earliest processes on the Earth. It can tell us about how Earth began, not just how old it is, but how it started out. And to introduce this story, let me start with this object, which is a meteorite. It fell near the town of Orgueil, I'm probably mispronouncing that, in southern France, near Toulouse, in 1864 actually, May 14, 1864. It was observed by the villagers. They were very surprised by it. Some people thought it was an earthquake. Some people thought it was a terrible storm, and so on. Anyway, this meteorite is very remarkable because of its composition, because of its chemical composition. This meteorite and a few others, which belong to what we call the Ci class of carbonaceous chondrites, we think are the most primitive objects in the solar system that we can get our hands on. Why do we think that? Because the composition of this meteorite is very similar to the composition of the solar photosphere. Also because it's been very little altered Most meteorites, if you look at them, it's obvious that they've been melted at least once. This one hasn't. Why? Because it's got a lot of water in it, weight percent water, way more water than is in the Earth currently today. It also has way more carbon than is in the Earth today. So it's preserving all these very volatile elements that would have left very easily if it had ever encountered a heating event. Now, one interesting thing about this meteorite, one interesting mystery for understanding the Earth, isn't a mystery anymore, but initially it must have been, is it has way more iron than we can see in the rocks that we can get our hands on today, from the crust and even from the mantle below. It has way more iron than that. And so the question is, if Earth is made up of objects like this, coming together and gathering and accreting and making up a planet, which we think, where did all that iron go? And the answer to that question is in the Earth's core. Most of the iron on Earth, iron is the most abundant element on Earth by mass, actually, and most of it is in the Earth's core. It turns out it's very important whether a planet has a core or not, even though we can't touch it directly. It produces the magnetic field, which is very important for us. It protects us from cosmic rays. It protects the atmosphere from erosion by the solar wind. And it's the interaction between the solar wind and the magnetic field that give us the aurora like this. This is taken from the International Space Station and looking towards Antarctica. And this is a remarkable aurora because this arm is reaching way out over the Indian Ocean, just a brief storm caused by a coronal mass ejection from the sun. So the core, of course, is towards the center of our planet. We have the crust, which is literally about the thickness of that line. You can also think about the thickness of the crust in relation to the whole Earth as the skin of an apple compared to the thickness of the apple as a whole. So the crust from which we extract all of our resources and do all of our drilling and so on is really very thin and quite different from the rest of the Earth. And so to understand the rest of the Earth, we do have to look beneath the crust in various ways. Below the crust is this blue bit called the mantle, which is also made of rock, of a denser kind of rock, but also oxides and silicates, as the crust is. And below that, the core, which is almost entirely iron, a little bit of light elements as well. Okay. Now, what's interesting about radiochronology today is that we can actually date when the core formed. So we don't think the core was always there. We think, as I said, the Earth formed from objects like that Orgale meteorite, which possibly had collected in the larger bodies out there. But the point is that the iron and the rock components were all mixed up as Earth accreted, and that there had to be an event of that iron sinking towards the center, a core formation event, the time scale of which we're not sure, but we can also constrain that with radiochronology. Now, the other interesting thing about core formation is that we think that the mantle had to be at least partially molten for that core formation process to occur. Okay? For the iron to sort of squeeze its way through the rock towards the center where it's attracted gravitationally, it has to make its way through the rock. And if the rock is still solid, it wouldn't be able to do that. So at least part of the mantle would have had to be molten at the time of core formation. Okay, how can we time core formation? Well, one of the things that happened as the core formed is that the iron dragged with it, scrounged out of the mantle as it went down, many elements, which are called siderophile elements, or iron-loving elements. Many of the metals, like gold and silver and so on, these are siderophile. Almost all of the inventory of gold on Earth, sad to say, is in the core. Leaving very much of it here at the surface, which is why it's so valuable. Anyway, tungsten is another siderophile element, which was almost entirely scrounged out of the mantle and transported to the core very early. Now, a lot of the tungsten, we do have tungsten in the mantle today, and a lot of that tungsten comes from radioactive decay. It's a radiogenic product, just like the argon you were breathing in before. And this the thing that decays, hafnium, has a very short half-life, only 9 million years. The parent is completely gone from the Earth, completely vanished a long time ago, leaving only the daughter, tungsten, in the mantle, radiogenic tungsten, which you can tell apart from the normal kind of tungsten. By measuring how much of this radiogenic tungsten is in the mantle, you can tell how many half-lives passed by before the core formed, and it's not very many. So we think the core formed very early on, 50 million years after the first solid grains in the solar system, so very quickly. This turns out to be important for the moon as well, because the moon, we can also measure how much radiogenic tungsten is in the moon, and we can tell that the moon formed shortly after the Earth's core formed. So again, maybe 60 million years after the first condensed grains in the solar system, after the birth of the solar system, if you will. Okay, so here's the moon. This is a nice image of the moon. This is taken by a satellite that's orbiting Mars, actually. This is NASA's reconnaissance orbiter, and it's looking back at Earth, and it's managed to capture the Earth and the moon in the same frame here. Now, the moon, people have wondered about the origin of the moon for a long time, too, and it turns out to be very intimately linked with the origin and beginning of Earth. The moon is a very special satellite in the solar system. It's not the biggest moon in the solar system. Ganymede is bigger, but in proportion to its parent planet, it's gigantic compared to any other moon in the solar system. The moon is about 27% of the radius of Earth. Ganymede is only about 4% the radius of Jupiter, for example. People recognize that the origin of the moon is a very special problem. You can't explain it in the way you can explain a lot of the other moons in the solar system by gravitational capture or something like that. Recently, people have looked at the composition of the moon in new ways, looking at not only the abundances of elements, but also the abundances of isotopes of those elements, and found that the composition of the moon is remarkably similar to Earth. They're much more similar to each other in things like titanium isotopes, as it turns out, than they are to anything else in the solar system. So it really suggests that the moon was extracted somehow from the Earth's mantle, to be more specific. One hypothesis that gets close to explaining all these observations, including the mass of the moon, the angular momentum of the moon, the composition of the moon, is the so-called giant impact hypothesis, which is still, I would say, the leading hypothesis for the origin of the moon. And this shows several snapshots from a fluid dynamical simulation of a scenario that may have produced the moon. In the first frame over there, you see the proto-Earth as the larger sphere being hit by a Mars-sized object with a glancing blow. And what happens after this impact is that a lot of material is spewed out into orbit around the Earth. It's a very violent event. And here you see this material being spewed out into orbit around the Earth, and eventually some of that material coalescing to form a moon. So you do find a moon forming out of these fluid dynamical simulations. Actually, between frames, there are several orbits in between. They're just not shown. What you see, the reason this is important for the origin of the Earth as well, is that it's given us a new perspective on how Earth grew to its present mass. It's emphasized the importance of large impacts in planetary accretion. And this is a relatively new discovery. For a long time, people thought that planets grew very gradually by the addition of very small little grains, which leads to a relatively cold start. But giant impacts, it turns out, are almost inevitable, no matter what planetary system you're talking about, because of something called oligarchic growth. As the planets are accreting from smaller bodies as they're orbiting the sun, the larger bodies grow faster than the smaller bodies. Why? Because they have a gravitational field, and they tend to pull the smaller bodies towards them, and so large bodies grow at the expense of small bodies. And so the end of planetary accretion, in almost all the simulations that are done now, you end up with large impacts of sort of similar-sized bodies at the end. So we think this is a generic process. And it's very violent. It produces a lot of heat. The colors here represent temperature, and we know something about impacts, and we know that they generate a lot of heat. One of the things we'd like to know, though, is how much melting did this produce? Did this actually melt the whole Earth? Did it produce a magma ocean? How deep was that magma ocean? These simulations can't tell us because we need another bit of information. We need to know how hot the Earth got, yes, but we also need to know what the melting point of rock is. And we need to know what the melting point of rock is at pressures of the interior of the Earth. And the Earth is a very big place, and pressures are very high, and that's why it's difficult to find out just how much of the Earth was melted by this event. This is just to say that we do know something about impacts. We've studied them quite a bit now. This is the Chicxulub impact, which most certainly did impact the Earth on the Yucatan Peninsula. It most certainly did that 65 million years ago. To what extent this killed the dinosaurs, we're still arguing about. But it did hit at the right time. This is an artist's rendition from NASA. And they do try to get the details of these right, the sort of relative size of the meteorite compared to the height of the clouds and so on. Over in the top right there is how we image the crater, this particular crater. It happens to be buried today, but you can image it with small deviations in the Earth's gravitational field. As you're standing over the crater, you weigh about 1 part per thousand less than you do when you're standing at the rim. And with very sensitive instruments, you can measure this. And that's the map that results from those sorts of measurements. Okay, so we know about impacts. We know they generate a lot of heat. But how does the heat generated compare to the melting point of rock? And how can we find out? We need to find that out at very high pressure because most of the Earth is at very high pressure. This is just a pressure scale for comparison. And what I've done is I've made the pressure go up in increments of factors of 1,000 from a millibar at the top of the stratosphere to 1 bar here in this room at the surface of the Earth to 1 kilobar at the bottom of the sea. This is actually at the bottom of the deepest part of the sea, the Challenger Depth and the Marianas Trench. Most of the seafloor is much lower pressure than this. The bottom of the mantle is 1,000 times greater again, about a megabar. And the center of a brown dwarf is about a gigabar. So at least in this scale, a typical pressure for the inside of the Earth, where we need to find out the melting point of rock, is closer to that of stars than it is to the familiar surface conditions that we know. Well, there are lots of ways to get at this. How much heat do you need to melt the Earth? And experiments can tell us something. So the limit of experiments today is around about a megabar, maybe a little bit beyond. But these experiments are very difficult. The information you get out of them is quite limited. We've taken a different approach, which is to take the equations of quantum mechanics and solve them and predict what the melting point of rock and other properties are at very high pressure. To get us thinking about that, let's think about physics at the atomic scale. The Earth, like everything else, of course, is made of atoms, and every atom has a nucleus and an electron cloud. Okay? And the electrons are positively charged, and the nucleus is, the electrons are negatively charged, and the nucleus is positively charged, and some balance between those forces make a chemical bond, like you might get at ambient pressure in this room. As you apply pressure to this system, though, what happens? The atoms start to overlap. The electron clouds start to overlap, and because the electrons have the same charge, they start to repel each other. Okay? So balancing this pressure that's squeezing the atoms together is an opposing force due to the repulsion of the electrons as they overlap. Okay? Now, if that's all that was going on, it would be very simple to calculate what that force is, and we could work out how much the density of materials change as you apply pressure, how the structure changes. We could work out melting points. We could do all kinds of things. But that's not all that's going on. Why? Because as the electrons repel each other, those electron clouds, which started off as nice perfect spheres, actually start to deform. They start to change their shape. And the change in shape is not simple. And it's due to two things. Correlation. Electrons tend to avoid each other because they have the same charge. And also because of exchange, something called the Pauli exclusion principle, which says that two electrons can't occupy the same state. And that tends to make electrons avoid each other as well. So what we do to solve this problem is we solve the equations of quantum mechanics. And I've given the basic equation of quantum mechanics here in its simplest possible form. I've eliminated time dependence, reduced it to one dimension. And what it is, in essence, is a statement of conservation of energy. That's one way to think of it. We've got the first term here, which is kinetic energy of the electrons. We have the second term, which is potential energy of the electrons, represented by V. And we have total energy, E. So kinetic plus potential energy equals the total energy. The psi is the wave function. This is related to the probability of finding the electron at a particular point in space. Okay? And let me say something more about this being the kinetic energy. Okay, so what is this? This says, the first thing says to take the gradient of the wave function. Okay, how much does the wave function vary from one place to another? The second operation says to take the curvature. How much does the gradient vary from place to place? Okay. Now imagine an electron as a wave. We know that in quantum mechanics we don't have particles, we have waves. So imagine an electron as a wave. As you squeeze the electron together at high pressure, the curvature of the wave gets tighter and tighter and tighter. And so that kinetic energy increases. And so in the end, it's a balance between kinetic energy and potential energy that make up the bonding and the changes that we get in material properties with increasing pressure. All right. Now, one of the things we can get out of these equations are the forces acting on the atoms. And if we can calculate the forces on the atoms, then we just solve Newton's second law, F equals ma. We know the force, we know the mass. We can calculate the acceleration, and so we can get the motion, atom by atom, of what's going on in a material at high pressure. This is a movie of a simulation based on the equations of quantum mechanics and solving F equals ma that my colleague John Broadalt at UCL did. And what we have, the setup here, is a crystal next to a liquid. So we're looking at the melting of rock. Okay, we've got crystalline rock on the left, and we've got molten rock on the right, and we're going to see which one wins. You can tell the one on the left is crystalline because you can see rows. The yellow ones might be easiest to focus on. The yellow ones are arranged in these nice planes, and on the right, you don't see those planes at all. It's completely disordered. Okay, so and as you run this forward, this is at a temperature of about 5,000 degrees, which we might expect, deep in the magma ocean, and a pressure of about 1 megabar, similar to that at the bottom of the mantle. And as this the atoms are moving around a lot, that's related to the temperature. Temperature is directly related to the velocity of the atoms. And as the simulation progresses, the crystal survives for a long time. The atoms are jiggling around, but you can still see the planes. And just about now, those planes are starting to be destroyed, and the crystal eventually melts. And so by doing simulations like this, at a series of temperatures, we can work out what the melting point of rock is. Okay, let me go back to this. All right, good. Okay, so what have we learned by doing simulations like this? Okay, so here's the traditional view, and this is the view that explains melting that we see in Earth today. All right, what we have is two curves. All right, temperature versus depth. The gray curve is temperature in the Earth. Okay. And it turns out temperature in the Earth increases slightly with depth because matter is being compressed and that heats it up. We compare that to the temperature at which rock melts, the melting curve, and we see that the temperature in the Earth is above the melting curve only at very shallow depths. All right? So this means that melting is limited to very shallow depths, as in the red bar here, and this explains most of the melting we see on Earth today. Turns out most of the melting on Earth today goes on under the sea. This is 90% of all volcanism on Earth is underwater, actually, and this is a picture of an underwater volcanic eruption from one of those remote vessels. Now, what we found is that as you go deeper in the mantle, though, as you go to much greater depths than the magma genetic zone that we have today, just the upper 100 kilometers, go all the way down to the base of the mantle, you get a very different picture. Okay, two things are different here. One is that the gray line is much steeper now. And the reason it's steeper has to do with the physics of molten rock. It turns out the molten rock has a much steeper adiabatic gradient. You compress on it the same, and you get a much greater increase in temperature. So the adiabatic gradient in a magma ocean is much steeper than in the Earth's mantle today. The other thing that's different is the melting curve, the point at which rock melts. That curve is much less steep. It starts out steep, but then it starts to turn over like that. And it turns out the reason the slope changes like that, or rather like this, is because the liquid is getting denser. And it's getting denser faster than the crystals are. And that's what causes the slope to change like that. So this gives us a very different picture. This gives us melting all the way through the mantle and complete melting of the entire Earth. Now, this has really interesting implications, one of which is that if you have a completely molten Earth, it turns out another interesting aspect of the physics of molten rock at high pressure is that it's electrically conducting. Now, people have wondered for a long time, how do you get a magnetic field on the early Earth? We have evidence of a magnetic field preserved in the rock record going pretty close to the beginning of the Earth. And how do you do it? You could actually do it by convection in the magma ocean instead of the Earth's core, because silicate liquids become electrically conducting. This might have other interesting implications. Of course, so this magma ocean sets the initial condition for Earth's thermal evolution. It's cooled since then, and what we would like to see is some fossil evidence of this magma ocean. This is one possibility for finding this fossil evidence. We have what happens as it cools is that it starts to crystallize. And one of the things we'd like to know is whether those crystals are denser than the liquid or lighter than the liquid. And one of the things we found is that the crystals deep in the mantle turn out to be lighter than the liquid. So the liquid sinks to the very base of the mantle. The reason for this is similar to why icebergs float. Icebergs float partly because ice takes up more volume than water does, but also because it excludes the salt. Okay? So the seawater surrounding this iceberg is more rich in salt than before the iceberg froze out of it. In the same way, silicate liquids take on more iron as crystals freeze out of them, and that makes them denser and makes them sink to the bottom. Some of these ideas were taken up by Lars and co-workers, and this is their cartoon of how magma ocean evolution might have proceeded. We start out with a completely molten Earth. We start crystallizing from the middle, actually, which leaves us with a bottom yellow magma ocean and an upper yellow magma ocean as well. And after a while, you get liquids sinking to the bottom, as shown in that first slide there, and you form these areas which have different composition indicated by the darker gray. And that's because the liquid has a different composition from the crystals that are freezing out. And you end up with a situation like this, where you have these piles of darker gray material left over as fossil remnants of the magma ocean. One of the interesting things is that seismologists see evidence for such fossil remnants at the base of the mantle today. These are called large low shear velocity provinces. There's one under the Pacific and there's one under Africa. They're right on top of the core mantle boundary. They're several hundred kilometers thick, and they have very sharp sides, which means they must have different chemistry, and we still don't know what these are. They're there, the seismologists see them, we just don't know what they're made of. And a fossil remnant of the magma ocean is one possibility for explaining what these are. And let me just end by saying that this, I think, is just the beginning of a large range of questions that the magma ocean opens up to us. Something I've talked about, how crystals settle out of the magma ocean, how you can get a lower and upper magma ocean layer, which might have very different histories. Some of the questions that we still haven't addressed yet are, for example, the atmosphere overlying the magma ocean. Earth's first atmosphere may have been a silicate atmosphere in equilibrium with this magma ocean. It may have been a vaporized rock, actually. Another thing, the oceans may have come out of this magma ocean because the magma ocean is able to take up a lot of water, has very high solubility of water, and so the water may have been expelled from the magma ocean. Okay, I'll stop there. Thank you.